Welcome to this video on graphical misrepresentations of data. Unless otherwise specified, all images used in this presentation were copied from Sullivan, Fundamentals of Statistics, 5th edition. Statistics versus the truth. There are many famous quotes that talk about the relative accuracy of statistics. American humorist Evan S.R. says that statistics is the only science that enables different experts to use the same figures to draw different conclusions. Mark Twain famously said, "There are three kinds of lies: lies, damned lies, and statistics." Statistics often gets a bad reputation as people claim that data can be manipulated and displayed in such a way as to support any argument. One way to be on your guard against being misled by statistics, and specifically by graphs, is to learn how graphs can be misleading and deceiving. First of all, let's ask ourselves, why do we use graphs? The purpose of graphing data is to allow humans to absorb information more quickly. Look at the two images below, which contain the same information. Which image is more easily and more quickly grasped? To answer this better, try to find which color has the highest frequency. First, let's look at the table. It might have taken you a minute, but eventually you probably realize that the color yellow has the highest frequency. Now look at the graph. Did it take you longer, shorter, or the same amount of time to figure out that yellow was the most highly represented of the colors on the graph? Chances are it was easier for your brain to process the graph than it was to process the chart. If you can imagine that instead of only having 4 rows, there were perhaps 20 or even 100 rows, then you can really appreciate how much easier it is to absorb information when it's given to us in graphical format. Misleading versus deceiving. Graphs that unintentionally cause a reader to misinterpret data are called misleading graphs. Graphs that intentionally cause a reader to misinterpret data are called deceptive or deceiving graphs. How graphs can mislead and deceive. Axes with an inconsistent scale lead readers to draw incorrect conclusions about the graph. When the vertical axis starts at a non-zero value, the reader may draw incorrect conclusions about the relative sizes of the bars in the graph. Graphing numbers rather than percents can misrepresent reality. Also, three-dimensional graphs and pictograms can often misrepresent the relative size of categories represented by the graph and are unnecessarily distracting. In the remaining slides, we will look at examples of each of these misleading or deceptive graphs. Let's start with this first graph. Pause the video, take a minute to look at this graph and see if you can figure out why this graph is misleading. Did you notice that the horizontal axis of this graph has increments that are in units of 10 until it gets to 90, and then all of a sudden, the increments change. First, it goes from 90 to 99, which is an increment of 9 units instead of 10, and then it goes from from 99 to 99.9, which is an increment of only 0.9, and so on. Then the increment becomes 0.09 and 0.009. Clearly, these increments are not all the same. The graph of the last 4 tick marks really should only span a single tick mark, which should go from 90 to 100. That means that this line over here should not really be visible at all. The graph should go right from here, and then it should go all the way up here in the span of a single tick mark. How about this graph? Take a minute, pause the video, and see if you can figure out what is misleading about this graph. Did you notice that the y-axis doesn't start at 0? The bar on the right is more than 3 times the height of the bar on the left, leaving the reader to assume that the tax rate more than tripled in a single year. But is this true? In reality, the tax rate in 2012 was 35%, and the tax rate in 2013 was 39.5%, which represents an increase of less than 13%. How about this graph? Pause the video and see if you can figure out what is misleading about this graph. Again, we see that the y-axis does not begin at 0. Instead, it begins at 30,000. One way that people will correct this misrepresentation of data is to use this little symbol right here to show that even though the graph starts at 0, there is a gap here between 0 and 30,000. While this is technically correct, it can still leave the reader to draw erroneous assumptions about the relative height of these bars and the overall trends. So generally speaking, even though this is technically correct, this sort of thing should be avoided. What is misleading about only displaying the number of people in poverty rather than the percent of the population that is living in poverty? Pause the video and see if you can think about why that might be misleading. The population as a whole could have increased, causing the number of people living in poverty to increase, while the proportion of impoverished people could stay the same or even decrease. Therefore, it is preferable to graph the percent of people living in poverty rather than an actual count. That way, it doesn't matter if the population as a whole is changing because you're looking at the proportion of people who are living in poverty. Notice also that this graph has been changed to a time series graph instead of a bar graph. Numbers versus percent. In the recent COVID-19 pandemic of 2020, the news reported the number of cases in different countries. What is problematic about comparing numbers in the United States and Italy? Pause the video and see if you can think of an answer. When we look at the land area of the United States versus Italy, we can see that Italy is a much smaller country. More important than area, however, is the human population. At the recording of this video, during the time of the pandemic, the population of Italy was 60.36 million, while the population of the United States was 328.2 million. This means that the population of the United States was more than 5 times that of Italy. So when you start comparing just numbers of new cases in the US versus Italy and suggesting that the number of new cases in the US was surpassing that of Italy, it really was an unfair comparison because the United States in both population and just geographical area is just so much larger than Italy. Problems with pictograms. What problems do you see with this graphical representation of data? Pause the video, write down your answers, and then unpause the video to see if you are correct. Compare the vertical scales of each bar to see if they accurately depict the given percentages. First of all, it is unclear whether the bars include the roll of toilet paper or not. Is the roll of toilet paper acting simply as a label, or is it part of the bar itself? We're not really sure. Unfortunately, whether or not you choose to include the toilet paper roll as part of the graph, the vertical scaling is still incorrect. Problems with pictograms, area versus height. In 1991, there were approximately 10 million soccer participants. By 2009, there were 14 million soccer participants. Does this image accurately represent these values? Why or why not? Pause the video, write down your thoughts, and then unpause it to see if you were correct. A person looking at this image will automatically compare the area of the two soccer balls, not the height. Unfortunately, in this image, neither comparison will lead the reader to the correct conclusion about the relative number of people who participate in soccer, that is 10 million versus 14 million. Comparing the two areas in fact, is even more misleading than comparing the height of the two soccer balls. The area of the soccer ball on the right is more than 4 times the area of the ball on the left, representing a more than 300% increase in soccer participation. However, in reality, there was only a 40% increase. Making a two-dimensional image three-dimensional. Which of these two images more accurately portrays the data? Pause this video, look at the images, and write down your answer. Then unpause the video to see if you are correct. Let's take a closer look at the three-dimensional graph and compare the relative sizes of the two blue wedges. From the three-dimensional image, which of these two blue wedges appears larger? Not a high school graduate or some college, no degree. When we look at the two-dimensional image, we can actually see that not a high school graduate represents 12% of the pie, whereas some college no degree represents 17% of the pie. However, because of the forced three-dimensional perspective, it would appear that not a high school graduate was actually a much larger wedge. Therefore, this is a misrepresentation of the data we're given. The pie wedges closer to the bottom of the image appear larger than those at the top because of the three-dimensional perspective. While the three-dimensional perspective may cause the pie chart to look cooler or seem fancier, it is actually misleading to the reader. Here are some guidelines for constructing graphs. The increments between tick marks should be the same on all axes. Scales for comparative graphs should be the same. The y-axis must start at 0 because readers usually assume that the 0 point is at the bottom of the graph when interpreting visual representations of data. When comparing populations of different sizes, it's best to display the percent rather than real numbers. Lastly, it is wise to avoid three-dimensional graphs and pictograms.